Hello, Netrasri. Hello.
Yes,
Am I audible?
yes, sir, you're audible.
Thank you. I think we can start the class, and later, if somebody wants, they can see the recordings.
Okay.
Yeah. 1 minute. So you can see the screen, right?
Yes, sir.
Yeah. So 1 minute. Just. So what we are discussing in the last class and what we are going to discuss in the today's class was, so before to the last class until week 8, we have discussed the classical thermodynamics. One second. Yeah. So from the last week, say suppose from the week 9, we started discussing the statistical thermodynamics. So in the last class, we have discussed the what do you mean by macrostate and what do you mean by microstate, and if the given system has three macrostates and how many microstates we can see in each given system, then we have defined the thermodynamic probability. Which is the occurrence of microstates in the given macrostate, so which is nothing but and so on. So where n number of particles and n1 defines the number of particles in the energy state 1. So from this example, I mean from this thermodynamic probability formula, so we further carried out these equations phi of so from using the Stirling approximation, and then comes the Boltzmann and Planck postulates. So we have come to the equation which says this is sigma. So this is nothing but again partition function. So what does it says? This was probability of ith particle in epsilon ith state. So from here, then after taking the partition function and after doing all the Boltzmann-Planck postulates, we came to the equation of this, and then from here we came what is W, and to the end we got the equation of one second, and we got the equation of this. I'm just revising what we discussed in the last class. S by Q equal to the total energy. From here we got what is the beta. So to at the end we got from to this equation to here we got, after calculating from here the what is beta and all, so we got it by So once we have this equation and we know the partition function, then we have derived the thermodynamic quantities like U, Gibbs energy, and entropy and all. So by doing all this, we got into one formula, and then we have done for the monoatomic gases using the quantum states. So we got the equation of Q equal to 2 pi m. One second, just 2 pi m kT by h square whole power 3 by 2v. And then from this equation we got the E as 3 by 2 nkt, and then we found out that S equal to nk ln q plus E by t. So this is the final equation which we ended last class. And in the week 9, if you see, we have the Gibbs paradox. So what does the Gibbs paradox happening or occurred was, so suppose in the we know that entropy is extensive term, which what does it says was, if we increase the volume to 2v and if we increase the number of molecules in the system to the, as these both are extensive properties, you know, in the classical thermodynamics we discuss extensive properties will increase by increasing the system size. So then naturally the system should also increase like this. So this is what expected from the classical thermodynamics. So then when I applied this equation, so we got this one here. So what we will get it was, so we got S equal to 2s, but additionally we got some extra term. So it's like S dash equal to 2s plus x, which is not equal to 2s. So it is not able to prove the classical thermodynamics. So why it doesn't prove the classical thermodynamics was, so the, see, this all the equations were arrived from this equation. If you remember, this is the starting equation. From here we found out what is alpha and what is beta by applying the Boltzmann Stirling approximations and all the things. At the end you got, this is the equation, which what does it says was, the entropy is not equal to the in the extensive term. So to overcome this, it means what the Boltzmann done was, he thought that okay, there is some mistake in the thermodynamic probability assumption itself. So then he recovered, he rediscovered all the equations, and he thought that okay, can we give any new term to just to prove the classical thermodynamics formula of this one. So then what we have was, so initially we have this equation. So if you see in thermodynamic probability, what we do was, we say that particles are distinguishable. So this is one of the assumption which was taken in thermodynamic probability in the initial days. So that's why we had WD as distinguishable, which is nothing but n factorial by, this is the basic equation which we know. So this can be written as like this. So now whatever we discuss, it is in the form of energy states. Like if it is in the energy state 1, epsilon 1 and epsilon 2 and epsilon 3. So now I am just considering only one energy state. Assume that this is the energy state of L. I can write it as L, and say it has degenerative steps, degenerative folds. Say suppose it has different folds like 1s 2s orbitals. Okay, so now we need to understand that, say suppose there is one EI which has only one fold, and there is EJ which has two folds. It means the molecule in a single, suppose what we discussed previously was, this microstate can be here, or it can be here, or it can be here, right? So if I go in depth of each energy state, say the energy state will looks like this. It have different folds of energy in this equal. Assume it as orbitals asp 1s 2s 2p and 3s. So what do I'm saying was it can go in this one, it can go in this one, or it can go in this one. So that's what I'm talking. Say suppose in one case it has only one fold, and I mean this is for the assumption. So assume that we have taken the threefold case. So if you take threefold case, so it means in the energy state of in the health energy state, we have three folds. So from the equation of entropy, what we know was S equal to minus nk sigma of. So this is the probability of ith particle in that energy state I. So now what I can write it was S equal to minus nk. So as now we are considering the energy of the health state, we can write rho L1 ln of rho L1 plus rho L2 ln of rho L2 plus rho L3 ln of rho L3. So now we know that here the energies occupied in this fold or in this fold or in this fold will be same. So it means rho 1 ln of rho L1 equals to, and so on. So that's why it will become as see for the how to say it, for the ease of the calculation we have taken only three folds, but the system can have up to the 10 to the power n degenerative folds, which we generate it as, which we normally refer it as GL. So now here we know that. So what does we have was here we have S equal to minus nk 3 rho L1 ln of rho L1. So we can write it as 3 rho L1 equal to rho L, because we know that the energy states are equal, which means rho L1 equal to rho L by 3, rho L1 equal to rho L by. So these are the generative fields, so it will be GL. So now the total equation will become as S equals to, so this will become as rho L ln of rho L1 by, sorry, this will become as rho L1 GL. So rho L1 is nothing but, so this will get cancelled. So this is the equation which we have. So from this equation we will derive how the S will come as. So now if I derive the equation, so we have the so now this is for the one health state, but we are taking the whole entropy, so it will be of sigma of L, like L different states of rho L ln of rho L by GL. You understand, right? So it's simply as sigma I rho I ln of rho I by GI, but we are discussing about the L energy level, so that's why I written as L instead of I. So this is for the only health state, and this is for the overall different states. So now we are going to expand this equation. So if you expand this equation, so if I expand this equation, it will be like S equals to minus nk sigma L nl by n ln of rho L by GL. So what I written here was, so rho L is nothing but number of molecules in this nth state divided by n. This is total n. So I made it in the full equation form. You can see this equation. Excuse me. Sorry. So now the equation which we have was, so the n is constant, so this and this will get cancelled. So now we have the equation of S in the terms of minus k sigma nl rho of rho l. So now, okay, one second. Before writing this equation, I can again rewrite this equation here also, like minus n, okay, sigma of nl by n rho of, so now this will get cancelled. Now therefore S equals to minus k sigma nl rho of nl minus I'm writing the ln of a by b is nothing but ln a minus ln b, so this minus will get plus, so plus k of sigma of nl ln of gl plus k of sigma nl ln of l. So this equation, what I can write it was, I will do addition with n and subtraction with n. So here what I will get was, I am taking k as common. Now if I take this one first initially, sigma nl is nothing but n. I am adding n and subtracting n from here. Then I am rewriting your equation as it is. Yes. Ln of gl, so it's minus, sorry, k not will be there, k won't be there, so minus l ln of nl. So here why I written was, so here nl only, so here the sigma is of l, so here this term will be the constant one, so that's why the sigma will only applicable to the nl. So nl means total number of particles in the L states, total L states, so that is nothing but overall number, so this will come as here, and then I am adding and subtracting with n, so minus n plus n to the next step, for the next step, and then I have rewritten the same thing, so here plus nl gl and the minus nl knl. So from Stirling's approximation, so what we are doing was, we are rewriting the equations which we know in the last class. So from the Stirling approximation, we know that ln of x factorial equal to this one. So suppose if I take the equation of this here again, so I can apply this part to here, to this one, so this will become as ln of n factorial plus sorry, we have n also plus n, this n is there, right? So now what I am writing was, now I will make this as sigma nl, and I am bringing this here, and I am moving it to back. So again here we are seeing the same sigma approximation. So now we have Stirling's approximation. So now what we have was, in Nothing wrong. Yeah, correct. So now we have what we have was is equal to k into ln of n factorial minus ln of sigma nl factorial plus sigma of gl power nl. So now this equation will become as is equal to k into ln of n factorial. So this will go down. So ln of sigma nl factorial. So this will be in the up. So now this will go as ln of n factorial plus. So if you expand the equation, so it will be like ln a plus ln b plus ln b plus so on. So it will be nothing but ln abc. So ln abc is nothing but if you are adding the sigma terms, then it will come as, and I am adding the both, so it will be, so I am writing only one ln for all the equation. So it will be k into ln of n factorial into pi of I glnl divided by, so here also same thing. So the final s equals to k into ln of n factorial into pi of gl by. So any doubts in this equation?
No, sir.
Okay, fine, thank you. So bear with me today, I have some cough, some cold. So now we know the equation of, so now we know the equation of S. So we already know the from the Boltzmann-Planck assumptions. So we know this equation, right, from the last classes. So now this equation, and we know this equation. So I will write here itself. So now what I will do was I will write as, I will equate both. So then what does it happen was, so now LHS are equal, so we need to make the LHS are equal, then we need to make the RHS equal. So then we will get, so this is the equation from the energy levels from the energy states. So this is the difference between the energy level equation and energy state equation. Now this is all based upon the distinguishable elements. So now say suppose we have two different atoms and we can distinguish which is which. So then these equations work out. So now say suppose we have, now we come to the, say suppose you have indistinguishable elements. Say suppose if I given a random state and if I ask you to put x comma o, so you can put it like this. Understand what I'm saying, right? So suppose what if you have the indistinguishable, so you don't know whether it is xo or ox or whatever, so you have two elements which you don't know which is which. So now I have given only one energy. So whatever we are talking in terms of energy level. Say suppose we have three different folds. So now we can put the two energy in one state. This is the first case. and this is the second case, and the third case will be in this, and then so there will be, this is one of the possible case, this is one of the possible. So total now we have, if I say that okay, in one energy state, so this is all one energy state, one energy state which has threefold generation, degeneration, and ask you to put, say suppose if you see it here, I am giving this state and I am asking you to put in the boxes the two elements which are indistinguishable, not the distinguishable, which are indistinguishable. So then we have the total 6 microstates. Okay. So what if it is distinguishable? Indistinguishable, indistinguishable. So if they are indistinguishable, we know that we have we have 6 cases. And what if they are distinguishable? Say distinguishable means we have two elements which are x comma o, and we need to put it in one energy state which has three folds. Say suppose this is one option, and this is the second one, and this is the third one. So there are three options here, and then we have the options of xo, xo, xo. So these are the three options. Again we, so this is the 4x, ox, ox. So if we consider the distinguishable, we have the 9 microstates. If we consider the indistinguishable, we have 6 microstates. So we can understand by now that in the initially when calculating the Boltzmann, calculating the equations for the W, so where he have taken this formula, so he has considering with the 9 microstate because this is the most feasible microstate. So he has considered this equation, and he has gone through to do the calculation, and he got some thermodynamic properties. But in general, if you have indistinguishable, because as in the chemical or in the biology field, the molecules are morely indistinguishable. So if it is indistinguishable, we can get only 6 microstates. So you need to work with the 6 microstates and not the 9, and we will see how the results will be for the 6 microstates. Say so now the thermodynamic probability for this 6 microstates will be, say suppose, where is the 6? Yeah, 1, 2, 3, 4, 5, 6. So now the formula will go like this. I will explain the formula again. NL factorial GL minus 1 factorial plus. So now if you take the 6 microstates from that example, so yeah, so how many number of particles we have? We have 2 particles. On how many folds of generosity we have? So we have 3, 1, 2, 3. So 3 minus 1 factorial. So here also how many particles? 2 minus 1 factorial. So it will be 4 factorial by 2 factorial into 2 factorial. So it will be nothing but 4 into 2. So it will be 6 microstates. So this is the formula for is for indistinguishable. So any doubts in this equation as of now? Okay. So now we have the indistinguishable element. So now once we have the indistinguishable element, so now it will be like cakewalk. So what we'll do was, so you need to remember whatever we are doing, it is for the only one energy state. It's not for the all. At the end we will add for the all. So we are doing for the nth state. Okay, you need to remember this one. So this is the equation, and now what I will do was, so I will expand the top one, GL minus 1 into, So by going on like this, so we are going from this. The one is nothing but number of particles, right? So 1, 2, 3, 4, 5, and it will go to NL. So here we will get NL cancel, and at the end we will get GL. So after the GL we will get, and so on. So divide by NL factorial GL minus 1 factorial. So now what I will do it here was, so this is explained in the class also. I'm just brushing the concept so that it will be clear why we are talking this. I will come to that point. So from here if I do it, it will be like GL minus 1 factorial. So now what I am doing was I am taking the GL from all the terms. So suppose if I take GL out of this equation, it will be GL. If I take into GL into X, so here GL into Y. Next if I take from this is GL into Y, and if I take it from here, one second. Yeah. Say from this equation, if I take GL out, it will be like GL into X, some equation. GL, it will be like 1 plus ln minus 1 by GL. So into, so from here if I take L comma, it will be Y equation into GL Z, and so on so on. We have the GL into GL into 1. So now see, suppose this is also U equation. So now there are total how many GLs will be there? It's up to NL. So there are NL GLs. So it will be like, so if I take, say suppose it is 2 into 2 into 2 into 2, 2 into so on. So it will become like 2 square, 2 cube, and so on. So if it is up to n, it will become as 2 to the power n. So that's what we are doing it here. So now what we'll get was GL power n. So this is the equation X what we are talking here. So it will be, I'll write one more term so that it will be easy for everyone. So by NL factorial. So now as we discussed earlier, so to make it a generalized equation, so in this equation, so what we can do was, so we are considering only the 3 folds, right? So basically it will have the 10 to the power of, in the biology system each one will have the 10 to the power of minus n fold degeneracy. So yeah, the number of particles will be more or less NL. So NL minus 1, say suppose this number is X, this will be like much bigger than the X, so this will get negligible, so it will become like 0. So 1 plus 0 is nothing but 1, 1 1 1 1, so on, it is 1. So that's why we got the final equation of WID equals to, now we need to, this is for the one state, and if you want to go for the all the states, so we need to do the multiplication of every state. So this is for the Lth state, right? So if I do want to do for the all the states, so it will be, so this will be the final equation, and if I can write it in the terms of, yeah, any doubts in this equation?
No, sir.
So now WDI equals to, I'm just rewriting the equation. So if I go back, I think, yeah, this equation, say suppose I am taking from here, I'm considering the energy levels of distinguishable and indistinguishable. Say thermodynamic probability between terms consisting of distinguishable and non indistinguishable. So if you see this equation, this will be n factorial by this one I'm talking about. So n factorial by phi of I, phi of L, and for the indistinguishable, so if I compare both the equations, so we will get sorry. So this is the correlation between the distinguishable and indistinguishable elements. So what is the differences? So now this many terms are we are increasing. So suppose we are using the formula for thermodynamic probability. With this equation, initially whatever we are doing, so we are taking the this many more terms. Okay, so that's why there is a in the last week class we have the Gibbs paradox. So where s is not equal to 2s, so it is equal to s equal to 2s plus some 2nk ln 2. So now from this equation what we will do was we will calculate the again the Gibbs paradox with the indistinguishable elements. So now from the indistinguishable elements, so we have p. So now what we can do was, this is the basic equation. So for indistinguishable, so from I am taking from here, indistinguishable is nothing but WD by n factorial. So this is n is total number of particles. So now we know this is nothing but again Stirling's operation will apply here. Stirling's approximation, not operation, sorry. So now we already know this equation from the last class, and see, this is what I think we have written it here. So this equation, so what I will write for this was k ln WD. This is from the distinguishable elements. So distinguishable is nothing but the previous one. So from this equation I can get this one. Sorry. So I am using the another color to understand that this is from the last class. So this is from today's class. Now what we have is, so if I mix both, so I am mixing this one and this one by taking nk common. So now the equation which we have is q by n plus e by t plus nk. So now if I apply the q value here, so it will be of nk ln of 2 pi m kt whole to the power h square for the monatomic gases I am talking about. So now this is the final equation for the monatomic gases, and we will make sure whether, so somebody says that okay some scientist has done some equations and says that okay we need to carry out the indistinguishable elements, because if we take the distinguishable we are getting the more microstates compared to the indistinguishable elements. So then they have done this and then they have come to this equation. So now we know that if you take the classical thermodynamics, V go to 2V, N goes to 2V, 2n, can S will goes to 2S. So then we will apply this equation here. So 2nk ln of 2 pi nkt. So I will write this as h again. So why to okay fine. So I will keep this element as assume for the sake of our time. I will write it as a. So then this will become as a power 3 by 2 into 2v by 2n plus we know that 3 by 2 nkt by t plus nk. So now here the tt will get cancelled. So now that n here will come as 2n and n here also will come as 2n. So before that I will write it as, so before initially, sorry, one second. So before this equation we need to make one more changes in the main equation. So that is, we need to rewrite the e also. We know that e is nothing but 3 by 2 nkt. So now I apply it here. Then this will become, assume this is a. So s equals to nk ln of a to the power 3 by 2 into v by n plus 3 by 2 nkt by t plus nk. tt will get cancelled. So then s equals to ln of a so the name of this equation was, this was generated by two people, Saker Road equation. So now we need to check whether these parameters, whether the thermodynamic properties be extensive in this equation also from the statistical thermodynamics. So now one second. So this is the equation. So 5 by 2 nk. So volume goes to 2v, number of molecule goes to 2n, then s should also goes to 2s. So by applying these two principles, we have s equals to 2nk ln of, sorry, s dash, I can write as s dash ln of a to the power 3 by 2 into 2v by 2n plus 5 by 2 2nk. So now I will take 2 common. nk ln of a 3 by 2 into v by n plus 5 by 2 nk. So this is nothing but this one. So now, so prove the extensive property. So you need to understand that, okay, initially the paradox or what we have, initially the assumptions whichever we have taken, it has taken the distinguishable elements and then it started for the equations with the microstate and microstate. So there we have so many microstates such that the result of classical thermodynamics is not in the line with the statistical thermodynamics. So then the few scientists has taken the indistinguishable elements and then they carried out the entropies and all the things to recheck that, okay, whether the formula which we have taken for the thermodynamic probability is right or wrong. So from here we understood that, okay, whatever the formulas we have taken, for the distinguishable elements, it will be n factorial so this will be the formula for the indistinguishable element. So any doubts up to here? So here we have overcome the Gibbs paradox, and initially we have in the last class we have discussed how to obtain the thermodynamic properties from the statistical mechanics. So that all becomes invalid now, and we will generate again the parameters for the what you call for thermodynamic properties. So any doubts in this entropy and how the extensive properties are mixing? I will explain it again. If no doubts, then we will go further. So I am assuming, I think I am audible. So I am audible, right? Hello.
Yes, sir.
Okay, fine. Thank you. So I mean, don't get confused with the so many equations. So basically, whatever we are trying to do was, our only goal is to find the, if you remember this thermodynamic probability. Sorry. So all the statistical mechanics starts with, so whatever we are discussing, this is all based upon the quantum. So because you have seen these formulas which are derived from the quantum mechanics. So initially, this all the states were carried through the quantum mechanics. So that's why this all the quantum mechanics states. So there the main assumption was to understand thermodynamic probability. So if you know the thermodynamic probability, initially it was this one, and then after doing the successive classical thermodynamics references, we got so you need to remember only this. Then again you can do the whatever the equations you need, and you can find out the sigma beta and all the partition functions and all the things. It will be the same. So now we need to find out. Okay, so we will go from the chemical potential. So we will find out, as sir said in the class. I will explain how we got the Helmholtz energy, and then chemical potential, and then the Gibbs energy. So now for the Helmholtz energy, we know that A equal to U minus Ts. So in the statistical thermodynamics, we will call A as total, U as not internal energy. So E is equal to U, which is nothing but total energy. So this is the formula. So once this formula, we know what is S. So E equal to T by. So I am taking this one. Which one? This one. I am taking this one. It's E by T plus NK. So now I got E minus NK T ln Q by N minus E minus NKT. So this will get cancelled. So now we have A equal to minus NKT minus so this is how the new equation comes. So then for the chemical potential, we know from Legendre transforms and the Maxwell relations. If we go back, so we will understand dg by dn at p comma t is equals to dA by dn at v comma t. So this is the equation from Maxwell relation. You can recheck your notes, or otherwise you can make this mnemonic diagram and you can even find out VT SP. So you can try with this mnemonic diagram also. For now, so now we know this equation. So from here, so this will go as minus nkt minus nkt ln of q by n. So now we are differentiating with the n. So the first term will get it as minus kt. Now here we are doing the two terms. Minus nkt ln q minus nkt ln n. So now if I do this all the equation, so you will get, now I am taking the kt common. Yeah, I can take the kt also common. That is far better option. So now if I apply the equation, so what I'll get was try it once. If you don't get it, then I'll explain it from here to here. So we need to apply minus 1 minus of n plus 0 because minus of ln q, and then this will come as 0, so it is constant term. So plus again 2 times, so plus it will come as ln n plus n into 1 by n ln n, so it will come as n cancel, so we have 1, so this one will get cancelled, so everything will get it. Just try it once. So from this equation what you need was you need to just apply the UV rule, so it will be minus 1. So from here what you will get was minus ln q, so from here it is like 2 terms, so which is ln n, and then you will get 1, so this one will get cancelled. I am taking the minus out, so if I take minus out, then it will be minus kt, and then ln q minus ln n, so it is nothing but ln q by n. And then I can take the Gibbs energy, which is nothing but this, and then you know the H is Helmholtz energy, which is nothing but U minus P. So this is nothing but U. You need to remember this, and we know that nothing but A. So G equals to minus nkt minus nkt ln of q by n, PV equal to nRT, so here we will use the nkt, so this will get cancelled. Now G is nothing but minus nkt ln of q by n. So which is again in proof with classical thermodynamics. So where we say that the G is nothing but the sum of all the states. So we are talking about the only one state, so it is n into u. So any doubts in these partitions? How to find out the thermodynamic properties? So you already know what is A, S, U, G, PV, and then if you want to find anything else, if you can make the equation in these terms, and then you can find out whatever you want. So it's basically what we have done in the classical only, the same thing. So now we have gone through the quantum mechanics or statistical mechanics, where we explain every terms in terms of thermodynamic probability, and by the limitations of saying that so as of now I have never said that particles are interacting. If you have seen while I am explaining the terms, I have said that we have distinguishable and indistinguishable, but I never said that these two molecules are going to react and it will get a new product or nothing. So I am not talking about any interaction. Particles are not interact. So what we have done was no story of particle interaction, and the energy term, if you remember in the starting class we have said we have taken this approximation to find out the beta. If you remember, this is approximation from where we got the beta. So we have written that okay, there are n particles, so suppose we have 5 different states and there are this many molecules, and we have started saying that okay, so this energy is 1e and it is 2e, so this is 3e and this is 4e. So can you tell me what is the total energy of the system will be? Hello. Yeah, hello. So, if if it's possible, I'm audible, right? I assume I'm audible. So let me check it here. Hello.
Yes, sir, you are audible.
Okay, okay, fine. So can anybody tell me, from the quantum mechanics assumptions, what you have taken was the total energy is E equal to sigma NIEI, and can you tell me what is the total energy here? So this is one of the question. I think it will be there in your assignment also. So if you know the energy, how much is here? If we given the two systems and we have given that, okay, this is the energy for each system, and how can you calculate the energy?
Tell.
So let me see. I too didn't do it. So it is 13 because you have two particles, right? 2, 1. Sorry, 1. So I'm missing anything. So there are total how many particles? 1, 2, 3, 4, 5. 1, 2, 3, 4. 1 second. So the energy of first state is 2 and there are 2 molecules, and the energy of second state is 1 molecule with 1. So it will be 2 plus 2 plus 3 plus 4. So 4, 4, 11. So you understand the 11? How we got the 11? Did I read the right or wrong? I think correct.
Yes, sir.
Yeah. So now what I'm telling was, if you see in the quantum mechanics, what you have done was, so we are calculating the energy in normal terms, but say suppose we have here two molecules. We are not talking about the interaction between these two. Okay, whether the molecules are repelling, attracting, or whether how far they are going. So we are not discussing any terms in this mechanism. So these all are the limitations or approaches which we have carried out using the quantum mechanics state. So to update this, Maxwell Boltzmann and Gibbs have come up with approach which is known as ensemble approach. So what do you ensemble means? Assemble all. To put it in the short form. So here we are considering the interactions of the system, and how to say it, here we are taking the more number of particles, which which means if you have more number of particles, it means you have more number of degeneracy. So all we all going to discuss here. If you remember the, I think in the classical also we have, I think in the, I think Restric, what is the name, Restric series or something, where we have taken the UAK plus UBK plus UABK. So that things we will explain it here. So what does the ensemble approach says was, so this is the recent or the current statistical thermodynamics, how the ensemble approach is used. Uh, so in ensembles there are different types of grand canonical ensembles. I think which will come in the, I think in the 11th or 12th class. I mean 11th week or 12th week, where we will have NVT, NPT, Q, V, T, on all the terms, different types of ensembles we'll get. We'll come more about the ensembles in the further classes. So for now, to give the outlet, say suppose we have one microstate. Assume this has one microstate with constant. All of these are constant. I mean the values are same, and there are number of particles. Are say suppose there are only 5 particles. I'm just giving the heads up. So this is the first microstate, and this is the time t equal to 0, and time t equal to 1. On the same condition, this might form like this, and time equal t equals to 2. And the same conditions, our box is same, everything is same. We started the randomization at t equals to 3. I mean t 3 seconds or 3 nanoseconds, 3 picoseconds, that also will come later. So just remember as a name, so it will come as 5 in the same another way. So in this way we will have n number of microstates with respond to the current corresponding to the time. Say suppose I am moving the molecules from, I mean at time t equal to 0 to time t equal to n, we can at each microsecond, at each picosecond or femtosecond or nanosecond, if you see the structural conformation, the system will change with respect to the systems. So what do you have? So these all are the tiny microstates. If you assemble them all and if you take the average, we can nothing but ensemble average, where we can get the properties of, where we can understand the properties of the system. So what is the difference between all these microstates was, see, so what does the ensemble original exam definition was? I will write the original definition by given in the class. Collection of systems which are macroscopically same but differ in microstate. So what does it says was, so we have all the different types of states. See, this is one microstate. If you see all are, say suppose it's like this. We have one macrostate where the molecule is in this form. I mean, one second, I will put it in a better example. Assume you have different energy states. So I have said that this is the energy state, and there are 2 molecules here, and there is 1 molecule here and 2 molecules here. So this is one macrostate. And now in this I will take the microstate. So where I have taken this microstate is how these molecules are moving, this 5. It can move in any way. So if you take on the level of macro scale, so we have only 5 molecules and the volume is same and temperature is same. Here also 5 molecules, volume is same, temperature is same, here also same. But if you see the conformationals inside, we can see the difference in the structural orientation. Okay, you can see the differences. So it says macroscopic state, it is same. Microscopically it is different. So I will give the best example. So when I said we have the system with microscopically same, it means NVT are the same and it is changing microscopically, which means we are changing the conformations inside, which is the function of Ri comma Pi. So Ri is nothing but the movement of the particle, and Pi is momentum, which is nothing but mass into velocity. Say suppose I will give the example of, as in the class in the same by sir, I will give it in a different form. If you see the alpha fold, if you have heard about the alpha fold, So it also does the same thing. What it do was, the basic concept of AlphaFold is same. So it will take the 2D structure, like unknown structures, unknown sequence, and it will randomly put it in the 3D format, and then it started to do the simulation. So it might be, it's like, say suppose it might go like this. So this is the stable conformation. So I started here, it may go down and it come to, okay, there is first metastate, metastate 1, it is metastate 2, and here we have metastate 3, here we have metastate 4, here we have metastate 5, here we have metastate 6, and we know that this is the lowest of all the metastates is, which is stable state. So what we will do was, we will run the simulation. See, if you take in macroscopic level, so suppose if I cut it like this, small lines. Assume it starts from 0 and it ended at, say suppose, 2000 microsecond. So if I do 2000 microsecond, so it means if I take the frames at every 1 nanosecond, you will get 2 into 10 to the power 6 frames, sorry, photos. Just put it in all in the single line, like one after one. So this is the first photo, second photo, third photo, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and all. In all this, the macro state will be same. It will have the same number of sequences. Sequence means number of amino acids will be same, and the volume is same, and the temperature is same. But you can see the conformational changes from 1 to 2. So you can see the conformational decline everywhere, and it reaches to certain position. So this is nothing but metastable state, which is will be the common state. So suppose if it is at to put it in an example, it came around at the 100, then 101 will be same, 102 will be same, 103 will be same, 104 will be same, and so on up to maybe say 200. Then up to 201 it starts degenerating, and again it might be this. So the metastable state is the one where the protein has the stable state and it has the lowest conformation, and it will stay there for a while, and then it will get pulled off. So you understand, right, the example what I am using. So to study this, we will study all these frames from 0 to 2000 microsecond, and then we will do the ensemble average to understand the protein conformational states. Any doubts in the example? For this, we need to know the what is the particles XYZ, because we are saying different conformation, and if it moved from one conformation to another conformation, with what velocity each particle has moved. So these two are the important terms in the ensemble average. So any doubts? Regarding the example? So if there are no doubts, then we will go to the, so now we will go to the ergodic hypothesis. So before coming to the hypothesis, so how the ensemble average, so average is always written like this. So if you see in any paper, if you see like this, it means average. So average of system A. So I have named the protein name A. Just assume for this the protein name is A. So what are changing? So it is changing, the position is, sorry, the movement of particle is changing, and the momentum is also changing. So from 0 to the last position, so the change in the position of the n particles, the momentum with respect to that particular position, and the probability density of to attain at that particular position. So what does this probability density will give us? So it will help in attaining the, say suppose we have 2000 microseconds, and if you take, you will get the frames of photos of 2 into 10 to the power 6, and if you do the calculation of every frame, the more or less the averages will be here, this position, this position, this. So if you take the probability here, it will be higher, 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 so higher and higher. So the mostly the result will be based upon this, okay, because it has a more number of frames. That's why we need to do the probability density function here. So the probability density is nothing but so this is nothing but partition function, partition function, and here H is nothing but total energy of the system. So total energy, which is nothing but H. So don't get confused with H and E. So we are using H here. So H is nothing but kinetic energy because the particle is moving with the potential energy. So we will write kinetic energy as K plus U. So we know that of the ith particle if it is moving, and then U, then P square by 2m, because momentum is nothing but mass into velocity plus U. Just remember this, of the nth particle at this position and this position, this is the probability, and the partition function in this function will be given by changes in the probability along with changes in the, so this is the ensemble average. So but the ensemble average is time consuming, we can't able to get okay how many frames are like this. So what we will do was, so because ensemble can be done for the more number of, say suppose the you can generate n number of confirmation and you don't know where to stop, so that's why we will apply the time case. So what we will do was time average instead of ensemble average. Ensemble average means, if you see the definition, collection of systems which are macroscopic same but different in microstate. So if I say I have 100 microstates, if you say 2000 microstates, and if I say 3000 microstates, say suppose I have 100 microstates, somebody has 2000 microstates, and you have run for the 3000 microstates, and somebody has run for 3 into 10 to the power microstates. So these all are the ensemble averages. Say suppose this is ensemble average of A at IIT Patna, and this is ensemble average of, say suppose, X college, so Z college. So can you tell me which ensemble can give you the best outcome? Forget about the time average for now. I have 100 confirmations, 100 microstates, somebody has 2000, somebody has, say suppose, 10,000, somebody has 3 10 to the power 6 microstates. So can anybody tell me which one has more possibility to understand the ensemble average or to get the proper value of ensemble? So we will get it from here because we have 3 into 10 to the power 6 frames. I mean, just assume it as photos. If you see here, we have the probability density. So if we have the more number of structures, then we can get the more probable density. So if somebody has 6 into 10 to the power 6, he has much more better ensembles, better thermodynamic properties and all the things compared to this all. So this is time taking and there is no limit for this equation. So for this, we got into the ensemble to time average. So what does the time average says was, limit t tends to infinity, I mean the time tends to infinity, we are taking the time from t equal to 0 to tau, a of Rn at time t comma Pn at time t dt. So this is the shortest equation which you can get, and this is nothing but, if I make it normal, so I equals to 1 to m, this is 1 m time m nth time, so it is of a power n at m at time t comma, So where m equal to number of confirmations. So nothing but say suppose t equals to 1000 seconds. Either you might save the confirmations for every say suppose, and you say that confirmations are saved for 1 millisecond. So you will get more confirmation, right? It's not 1000. So you need to remember that m is not always 1000. Okay, m is nothing but the time. So this is the shortest form of writing the ensemble average. So if you run for long enough, say if I say yesterday, this example, as we have ensemble average will be better at 6 into 10 to the power 6. In the same way, if you run for the long enough, and if you find it from the literature or somewhere, if they say that okay, the molecule has got into the equilibrium, and if you take the data at that position, ensemble average is nothing but time average. So that's why when you are running a simulation, we will run the time average, not the ensemble average. So that's what the ergodic hypothesis says is, if you run the simulation for the long enough, if you run the simulation, or if you leave the system for the long enough, if you run the simulation or system for long enough, then a ensemble equals to a time. So any doubts in this equation? So you understand the concept, right? Hello.
Yes, sir.
If you have any doubts, you can ask me in the middle itself. Okay. I mean, if you don't understand any equations or the concept, you can ask in between. Okay. No need to wait till the. Okay. If you have any doubts. So we have covered the most of the topics. So now we have last topic is of the class is interacting systems. We said that the Boltzmann has not considered the interaction between the two particles. So if we consider the interaction between two particles, if I given say suppose A particle and B particle in the box, what is the changes will happen was the A may react with the B. Sorry, if I have three particles, or A may react with the C, or A get repulsed by this one, or A can move freely. So there are different participations. I mean, there are different ways that A can interact with any other systems. So for that, we need to understand the partition function. So we know the partition function from the ensemble average is so this equation what I am writing here. So now we know that H is nothing but H, the total energy is dependent on the, this is total energy, which is nothing but kinetic plus potential, and we know that kinetic energy we can get simply by half mvi vi square, which is nothing but pi square by 2m. And for the internal energy, so now we have the different types of interactions for the don't think it is interaction entropy, it is internal energy. So if I take the system with the different molecules, if you remember the Van der Waal, what he has done was, so in the Van der Waal, to obtain the PV values for the PV, what he has taken was he has considered that there is a volume for the finite volume. If you remember, he has considered all the molecules are the beads or the balls, and he removed the length covered by this molecule like this. If you remember, this will be the equation, I think, plus a by v square. I think this is the equation. So what he has done was he has removed the volume occupied with small balls, and then he has removed the total interaction between these two by v square. Okay, so he has removed these equations like this for the Van der Waal, if you remember. But here we are considering the parts. So if you understand the interaction, so we can say there are equation between a comma b. So this is a, b, c, d, e, f, and a can bind with ac, and a can hit the wall, and then a can bind with c, can be with d, can be with b. This is the four-step interaction. Otherwise a, b, c, or a, b, e. So there are different types of interactions which you can see. So that's why the potential energy will always be sigma of I. So we are considering the two particles. So A can bind with B. If you take first molecule, and what is the interaction between the first molecule with the second molecule, and how far it is there. If it is very far, you will get the zero value because there won't be any interactions, and in the same way there won't be any assumptions. So then we have the three functions U3 R3. So this type of equations, and we can get the U4, U5, and so on. So we are considering higher order in the second order itself. So that's why we will get, if you neglect it, you will get R1. So I equals to 1 to n minus 1, j equal to I plus 1 into n u2 of r. So this is the interaction energy which we need to focus on, and we know the kinetic energy. And from the next classes, what we will do was what are the different types of interaction energy we have. Sorry, internal energy, which has bonds, angles, and then torsional, dihydrals. We'll discuss all this in the extensive, and then I will explain you what is NVT, and what are the different ensembles we have. And mostly my research is inclined in the same field, and I will show with the one example structure, like how the system will look like, how the system is carried out the simulations, and how we are studying the atomistic simulations. Okay, these things we can discuss in the, I think, the next class, and we can discuss the LJ potential. The graph looks like this, where we have particle x and y, and if you move the particle for the longest distance, the value will goes near to the zero. It means there is no interaction. And once you come molecule nearer, like this, and like this, it attains to some attraction position where it will have the highest binding energy. So this part is nothing but the more interaction energy. So once it get closer two atoms, once you get the two atoms very close than this bond length, so if you get the closer like this, the repulsion force between them increases. So this is called LJ potential. And then we have the electrostatic potential also, Q1 Q2 by R square. So, and you need to remember everything whenever you're talking about the interaction entropy. We are taking the only one atom, we are considering the nucleus atoms of that particular particle, because we are not considering the electrons, because electrons motion is very faster compared to the neutrons. So sorry, nucleus. So we are focusing on the nucleus and the nucleus interactions. So this is up to the class. If you have any doubts regarding this class, you can ask me. Otherwise, we have discussed all the parts which you can solve it for the, just let me keep it one second. Yeah, I think we have discussed all the things which you needed for the class, I mean to solve the assignment. And if you have no doubts, then we will solve one assignment problem which is in line with the, which you may get confused. Just give me 2 minutes. Yeah. So this is one of the problems, one of the typical problems which you have. So can you, hello?
Yes, sir.
So I think remaining all questions, if you listen this problem solving session or in the class, the mostly the questions are related to the ergodic hypothesis or the formulas, or like say suppose the energy states. So we have already calculated the how to calculate the energy states. So this is the formula we already know. So unless until mentioned it is a statistical mechanics or quantum mechanics, so I think the questions are asked from the quantum mechanics only. So you can use the total energy formula and you can answer the questions. So this is one type of the question which is there in assignment. So can you tell me the answer? What is the answer for this question? So assume this is one type of macro state. So they given the system macro state and with one micro state. So can you tell me what will be the what is thermodynamic probability? So you understand the question, right? So we have two particles. I need to fill in these micro states. So what will be the thermodynamic probability? So you need to remember that initially the thermodynamic probability is nothing but the number of microstates given the macro state. So this is the macro state, and I think in the last class, just 1 minute, I will come back to the problem again. So if you see it here, I think we solve the same problem here. In the same way, so we'll have 5 more minutes. I mean, take 5 minutes. Can you solve this question? You can see the question, right?
Yes, sir.
Yeah. Can you solve it and let me know the answer? I will also solve the question.
Sir, in fourth column, in first row, the box is empty, or is it there any
So which one you talk? 1 second. So you're talking about which one? This one.
fourth column,
Fourth column.
first row?
No, nothing. There is nothing.
There is nothing. Okay.
Yeah.
Okay.
So there are total like yeah. You can give me the close value also. You don't need to give me the exact value. If you have seen the assignment, the values will be in the lakhs. You understand, right? That point of you keep in the mind, because if you see this type of questions and see the answer, say suppose the options in the given assignment, it's like ABCD options. The answer is in the lakhs, so you should also get it in the lakhs. I'm just giving the hint. Can I solve it? The question. Have you understand the question? Hello.
Yes, sir.
So now, so what is the question given was thermodynamic probability of the following system. So they're asking you to find the W. So the definition of W is the number of microstates corresponds to a given macrostate. So this is the definition. So they are given one macrostate and ask us to find the thermodynamic probability. So now given X, how many molecules are there? 1, 2, 3, 4, 5 are there. O 1, 2, 3, 4, 5, 6 are there. So total boxes 1, 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So total boxes equal to 30. Now if I do that, so now I will take any one. So suppose first I will take this one. So first I will take big number. So now I want to put, there are 30 places and I need to fix the 66, and then the remaining I have 24. I need to place the 5. So this will be your answer. So it is nothing but, you can do it in the reverse also, or I will take the first this one and then I can fit this many. So it will be like 30 into 29 into 28 into 27 into 26 into 25 into 20 divided by 6 factorial into 24 into 23 into 22 into 21 into 20 divided by 5 factorial. So it's like W equals to 20 into 21, sorry, so W equal to 30, 29, into 720 into 120. So if you do this, I just did it. So the answer came was, one second, 2, 5, 2, 3, 7, 8. So there are this many number of microstates are possible. Any doubts? Have you understand the logic behind this question? I think I'm audible, right? I'm audible, right?
Yes, sir.
So what they asked was, they are asking to find the thermodynamic probability. So thermodynamic probability is nothing but the number of microstates of the following system. If you see, they didn't mention the microstate. So what they given was macrostate, and they are asking to find the, okay, what is the thermodynamic probability from this microstate. So how many macrostates you can obtain from this is nothing but the thermodynamic probability. So you have the 6 molecules of O and there are 5 molecules of X. Either you can fill first this one or that one, you will get the same combinations. So first you fill 30 of orange balls in 6 places, and then you are left with 24, and in 24 you need to fill the 5 places. Or you can take this one first, and if you do the probability you will get this value. So you don't need to get confused with this. So if it is only microstate as given, and if they ask the thermodynamic probability, so then you should remember that, okay, what is the probability of only this particular is, this is the total number divided by of particular one. Okay, if they ask a particular microstate. You got the point, right? What I'm saying? Hello.
Yes, sir.
So any doubts regarding the class?
No, sir.
If there are no doubts, then we'll wind up the class. And thanks for attending the class, Vishwajit and Netrasri. Thanks for attending the class.
Thank you, sir.
Yeah, thank you. Oh, thank you. You can leave the class. Thank you.